meeting is being recorded.
Hello, everyone. This is the Association of Women Geoscientists, Pacific Northwest chapter. We have a special talk tonight, which is Dr. Hannah Shamlu from Central Washington University. And her talk will be on timing is everything, pre-eruptive magmatic processes, and timescales for Mount Baker volcanism, Cascades, USA. You could see the picture in the background. Now, right today is Saturday, November 23rd, 2024. And for those that are looking at this later, this is recorded. So, I just want to say a little background from her. Hannah has been teaching courses focusing on volcanology at Central Washington since about 2022. Before that, she did an NSF postdoc at OSU after receiving her PhD at Arizona State University. She also holds a BS in geophysics from CSU Northridge. Quite a well-educated woman here. Her research interests mostly have to do with volcanoes and what makes them and their magma chambers tick. She's currently working on a project with Kelly Wall, USGS, and an older Cascade volcano, Goat Rocks. So she's got lots of videos with Nick Zentner, and yeah, we have more links on our site, and I'll just let her go.
All right, thank you, Mindy, and Marcia, future watching, I guess. Thank you for the invitation to speak today. I'm honored to be asked to speak with the AWG. So today I am going to be talking about Mount Baker volcano, specifically the work that my two master's students have completed for their theses. And before diving into the science of today's talk, I just want to make a note that there are a lot of names and unique meanings for this volcano, specifically by the Coast Salish peoples who have been stewards of this land since time immemorial. I want to show my gratitude to these people. And today I will be referring to the volcano as Mount Baker, but not out of celebration of white settlers, but rather just out of geographic convention. So the real stars of the show today are Desiree Cunningham here and Emily Yoder. So these are my two master's students who have recently graduated just in the spring of this year. Desiree has now moved on to becoming a mapper at the Kentucky Geological Survey. And Emily is in pursuit of PhD programs, but in the meantime is going to start working at CVO on a 180-day assignment. So we're very excited for both of these guys. And I also want to mention that this is a collaborative study. So I have a National Science Foundation grant with Western Washington University.
Sleep in the basement.
Oh wait, let's mute those people over there. Annette, can you mute your iPad?
Oh my God.
Okay, and so I just want to give a shout out to my co-PIs here. So namely Dr. Sue DeBari and Christina Wolowski, and then a special thanks to Dave Tucker, who has been really helpful in our field efforts and just knows this volcano inside and out. So thank you, Dave. Along with my students, I also want to recognize Ricardo Escobar Burciaga and Brendan Garvey. So these are two of Sue's master students who have now gone on and graduated. And a lot of my students' work builds directly off of these two master's theses. So a lot of the foundational geochemistry that I'm talking about today is thanks to Ricardo and Brendan. And then another shout out to Amanda Flory, which is one of Christina Wolowski's students who has provided us with melt inclusion work that I'll also mention today. Okay, so today is a Cascade story. So we are in the Pacific Northwest. All of you are familiar with the volcanic arc that we live in. So this is a map of that volcanic arc in the United States. And you can see there's a wide range of threat levels. So these are all active stratocones in the Pacific Northwest. I have the privilege and pleasure of living in Washington State, where I'm nestled in one of the most beautiful places on Earth, as well as has a lot of potential to study active volcanoes. So in Washington State alone, so here's Central Washington University, where I'm sitting right now. You can see we're really in the heart of all of the action, all of these active stratocones, specifically high to very high threat stratocones. So there's a lot of motivation to understand how these volcanoes work. So we're talking about Mount Baker specifically, so the northernmost volcano in Washington State. And Mount Baker, out of the 160-something volcanoes active in the United States, Mount Baker sits at number 14 in terms of threat level. And so that threat level is informed by a lot of different ways. So this is a hazard map of Mount Baker. So this pink area is basically the edifice of the volcano, where you can expect lava flows and pyroclastic flows. What is not shown on this hazard map, of course, is ash, which could extend to this entire area if we get a voluminous enough eruption. But something really to pay mind to is the heat maps here, which is basically lahar paths where lahars have occurred or could occur in the future. And you can see in the direct path of a lahar down these river drainages is a variety of population centers, namely like concrete, which is in a very high hazard zone, extending to tribal communities such as Swinomish and Lummi Nation around Ferndale here. A common hazard we speak about specifically to Mount Baker too is the presence of this lake, Baker Lake Dam. So if we were to zoom in on this dam using Google Earth in a satellite image, you can see that in the scenario that there would be a lahar maybe traveling down this side of the volcano, the idea is that there's potential that this material from the lahar could overtop the dam, leading to catastrophic failure and potentially affecting those communities downstream. So it's really clear why we have motivation to study this specific volcano. Okay, so here's a photo that one of my students took looking at the volcano north. And I just want to point out some of the main features. So of course we have our beautiful iconic stratocone. So this is Mount Baker. In the back, you can see these spiky peaks. That's the Black Buttes. So that represents an older period of volcanism prior to the main cone formation. And then right here, we have this little bump right here. This is Schreiber's Meadow cinder cone. So this is a young cinder cone that basically produced not only an explosive eruption, but also an effusive eruption. So we get a tephra and a lava flow, and this is one of the eruptive vents that we'll be thinking about today. Okay, so I am classically trained as a petrologist, so I care about minerals and geochemistry. So putting Mount Baker into the broader context of its eruptive lifetime. So these are argon ages of the volcanic field from Hildreth, 2003. And you can see, one, there's a lot of eruptive activity here, and two, our eruptive activity is as old as 1.3 million years ago on the left side of this plot, all the way to present day. And you can see there's a variety of chemical compositions. So we have mafic eruptions, we have intermediate lavas, as we expect at one of these stratocones. And then we even have caldera-forming eruptions that are producing highly silicic compositions. But what we're concerned about today is highlighted in these red circles here. So the most recent effusive activity at Mount Baker. And why we care about these units specifically is they represent the closest snapshot we can get to what the magma chamber looked like prior to eruption. So the most recent part of Baker's lifetime. So we're looking at 4 different lava flows, and I'm going to repeat these lava flows through this talk. Just so to orient ourselves, here's the summit of Mount Baker. This is a geologic map from that same Hildreth study. So we're thinking about the andesite of Dobbs Creek that erupted 119,000 years ago, the andesite of Dobbs Cleaver 105,000 years ago, and the andesite of Swift Creek that erupted 48,000 years ago. And notice these lava flows are located on the north part of the volcano. And then on the southern flank of the volcano, there's our little cinder cone again. So this little pimple is Schreiber's Meadow. that produced a tephra and a lava flow. You can see that lava flow actually extends into Baker Lake. And that lava flow had two compositional end members. It had a basalt and a basaltic andesite. And all of that chemical detail will come into, will make more sense as we continue through the talk. So we are in late Pleistocene to Holocene territory. So again, we're in the most recent effusive stage of Mount Baker. Okay, so I'm going to be showing a lot of magma cartoons today, and if you're a petrologist watching this, you are probably well familiar with the fact that we are moving away from this really simple model of magma storage. So we don't really draw our magma chambers like this anymore, where we just have a single homogeneous body that's all liquid and it's decapitated, it's just floating in the crust. Through decades of geophysics and geochemistry, we now adopt what's called a transcrustal magma mush system. Transcrustal meaning that it extends all the way from the mantle to the surface. Here I'm just showing the shallowest part of that mush system. But the word mush refers to the fact that our magma storage is dominantly crystalline, so it's mostly solid like a slushy, but we do have these more melt-rich or liquid eruptible pockets that are usually oriented in a sill-like geometry and can be interconnected. And that's what I'm trying to show with all these gray blobs here. So a couple things through a lot of research, thanks to master's theses, as well as publications, mainly led by Sue DeBari's group, we can actually add quite a bit of detail to this transcrustal mush system beneath Baker. So notice I've added a couple things to our cartoon here. So I have actual numerical values for magma depth. So we do have an idea of what depth these magmas are being stored at, thanks to mineral barometry, as well as melt inclusion work. And then I also have these different labels here, and I'm going to color code our little magma chamber here so I can point out some of the more key features. One, through geochemistry, we've been able to identify two mantle-derived magma series that are basically representing melts segregating from the moho beneath Baker. And so we have a high magnesium basalt series that is only erupted at the summit or near the summit of Mount Baker. And then we have a low magnesium series that is really only observed being erupted at Schreiber's Meadow. And then another key feature is this shared dacite reservoir. So we think that there's this laterally extensive, relatively felsic reservoir that's continuously tapped and shared between these two different vents. And then some other color-coded blobs on here are the gray. So anytime you see a gray or black, that's a basalt. Anytime you see a green is a basaltic andesite. So a lot of chemical variation within our transcrustal mush system beneath Baker. Okay, so all this detail hopefully will make more sense the more I talk, but the point of me sharing this with you is the fact that because we have such great extensive work on this volcano, we can start asking more specific questions that I'm particularly interested in, such as what processes actually initiate eruptions at Mount Baker. So we have an idea of how magmas are stored, but what is the process that tips the scale to actually cause magma to leave the crust and erupt on the surface? So that's question one. Question two is, what's the timing of that process? Like, what's the stopwatch? Are we talking about millennia, centuries, decades? And then lastly, how long are magmas stored eruptible? So again, we're thinking of mush. So we're thinking of kind of crystalline, icicle type material, but what is the window of time where these magmas have potential to actually exit and erupt? So these are the three questions that I'm interested in my research group, and it's also the questions that are driving my students' work and what we're bringing to this big collaborative study on Mount Baker. And so those three questions are going to drive the chapters of today's talk. So we're going to talk about, again, what's happening in the magma chamber prior to eruption, how long are those processes taking, and then what is the timing of magma residence? So how long is magma stored eruptible? And once again, because we do have so much foundational geochemistry and petrology done on this volcano, we're going to compare 1 and 2 across these 4 different lava flows through time. So we're going to look at a lava flow as old as 119,000 years ago to as young as 9.8 thousand years ago. Okay, so let's start with number one here. So what are the processes happening prior to eruption? So the way we're getting at that question is by looking at crystal cargo. So we're looking at phenocrysts and crystal clusters, or another word for that is glomerocrysts, as our record keepers. And so when I talk about Mount Baker lavas, I used to talk about them as messy, but I think a more appropriate word is they're just really chemically diverse. So there's a lot of chemical variation in our crystals. And so we've given our students this task of detangling this mess or this chemical diversity. And so the way that our students do that is one mineral phase at a time. So for example, I'm showing Sulphur Creek basaltic andesite lava here. This is from my student Desiree's thesis. And she's looking at plagioclase crystals at a time. And the idea here is to quantify the chemistry from the core to the interior to the rim of this crystal to get a sense of chemistry changing through time. And that allows us to make these chemical plots. So for example, I'm plotting magnesium here versus anorthite content. So a reminder that anorthite content is basically the major elements that make up plagioclase, so relative sodium, calcium. And the symbols here are corresponding to where that chemical analysis was taken spatially in the crystal. So is it a rim, is it an interior, or is it a core? And so what our students do with these plots is basically they start to identify chemical groups. So some of those chemical groups are very easy to see with the eye. So like just simple observation, you can say this is a chemical group. We have a little cluster here, a cluster here. But then there's some chemical groups that are less obvious. So our students rely on textural evidence, so textures of our crystals. And then they also rely on more than just one trace element. So we're not just looking at magnesium and plagioclase. We're looking at iron and titanium and a suite of trace elements that we collect on an electron microprobe, as well as a laser ablation ICP-MS. So through this protocol, our students assign these clusters, chemical group names, and then they move on and do the exact same thing with the other mineral phases present. So here we're looking at clinopyroxene. In lesser amounts, we do have orthopyroxene, and sometimes, if we're lucky, we get olivine in the basaltic material. But here we're showing clinopyroxene. So now I'm showing iron versus magnesium number. So again, magnesium number corresponding to major elements in the clinopyroxene. We have our symbols here, and then same protocol where our students are assigning chemical groups, which in this array of data maybe is not that obvious. So using, again, textural evidence as well as a series of trace element plots. Okay, so once the geochemistry of our crystals has been measured, then our students stop thinking about mineral phases individually and start thinking about them as co-crystallizing assemblages, meaning crystals that are growing together and are in equilibrium with some parent magma composition. So following just the petrologic methods of Streck 2007, for example, if we have a clinopyroxene, so this is clinopyroxene data down here, if we have a CPX crystal that's in the range, that has a magnesium number in the range of 78 to 80, we can equate that to being in equilibrium with a basalt. If we have magnesium number in the range of 74 to 78, that's a basaltic andesite. And then you can see where I'm going here, where if we have clinopyroxene from 68 to 74 magnesium number, that could be in equilibrium with a dacite. And so this information allows us to start thinking about our chemical groups across mineral phases as co-crystallizing assemblages that are from some parent magma composition. So through this method, we've been able to identify a dacite, multiple basalt flavors, as well as basaltic andesite. And so the point of all this is this has been done in like painstakingly detailed work by our students. So this is Brendan Garvey's work. This is Ricardo Escobar Burciaga's work. So these are Sudabari's master students who again set the foundation for the work that we're doing. And you don't need to digest the contents of these tables. The point is, I just want to brag for them of the amount of detail and thought that they've given this protocol and how beautifully done that they've been able to identify all these different magma components within a single eruption. And so I think a better way to visualize this is not through tables, but maybe through a simple pie chart here. So Through Brendan and Ricardo's work, they basically identified 8 distinct magma components that are continuously sampled through time. So if this is our key right here, this basically represents each color wedge represents a specific magma component. So we have a dacite, we have a couple of basalts, we have a couple of basaltic andesites. And then notice how our 4 different lava flows are erupting that same co-crystallizing assemblage through time, maybe with the exception of Sulphur Creek that has these 2 new assemblages that are not identified in the older lavas. So the point of this is through all of this geochemistry and petrology, we are seeing that the magma mush beneath Mount Baker is this well-established factory that is repetitively erupting the same compositions through time. So it's like this well-oiled machine. So that's great. That's the foundation we're building off of. But remember, my students are concerned with what is the process that tips the scale to actually get magma out of the crust. So the way we get at that question is through zoning patterns. So we now have an idea of what our different what magmas our chemistries of our zones represent, but now we want to look at the sequence of events prior to eruption. So let's say we had, this is a simple cartoon of a plagioclase. Let's say we have a core that is from our dacite group, and then we have an interior from our basaltic andesite group, and then our rim, or the final period of growth our crystal experiences before it erupts, is in equilibrium with the basalt. So at face value, we have a sequence of magma components that our crystal is in equilibrium with, but that's not really giving us detail on the process. So this is a start, but we want to push our geochemistry a little further. So we start constructing plots that look like this. So this is plagioclase data, and this is strontium over barium versus titanium. Or another way you can think of this plot is this is compatible elements in plagioclase versus incompatible elements in plagioclase. And so what you're looking at is these dashed lines is basically predicted anorthite content in a plagioclase in equilibrium with a mafic liquid versus a felsic liquid. And then our symbols here, these are all plagioclase analyses, color-coded by those different magma components that we identified in the previous slides. So the way to read a plot like this is if your data is plotting along one of these trends, that's indicative of crystal fractionation. So that's just the natural evolution that a plagioclase will take in equilibrium with a mafic or felsic liquid. So some encouraging news is that our dacite data here does follow that trend. Our basalt data slightly follows that trend. What's interesting is notice our basaltic andesite data that's color-coded by green is directly in the middle of our dacite and basalt. And so if we have data that's intersecting these trends, that's indicative of chemical mixing. And so this plot is actually telling us that this basaltic andesite that we are seeing commonly represented in our crystals is the direct product of mixing between this dacite, or these red data, and the basalt data. So we're seeing some evidence of chemical mixing. So we're starting to get closer to that process that we're so interested in. But again, we want to take this a little further. So this is another plot, still plagioclase data, but now we're looking at iron versus anorthite content. And the reason we make plots like this, because again, if you're a petrologist and you're thinking about plagioclase, you know that there's multiple ways to change your anorthite or your major element chemistry signal. So anorthite is temperature dependent. So in a very simple world, if we see an increase or decrease in temperature, then that will be associated with a change in anorthite, but not necessarily a change in iron. Iron instead is sensitive to chemical mixing. So if we see a trend that follows this direction on this plot where anorthite content's changing and iron content's changing, then that can be indicative of a chemical mixing or mafic recharge. And so side note, I just want to make it clear what I mean by thermal versus chemical mixing. We will come back to this plot, but what I mean by these processes is if we're looking at our magma cartoon again, what I mean by chemical mixing is if we have an injection of hotter, more mafic material into, say, a resident cooler, maybe more silicic magma, The mixing of that mafic and felsic material can actually lead to an intermediate magma composition. So there's actual mass exchange happening here, and that's what we mean by chemical mixing, or often referred to as mafic recharge. Thermal mixing is when we still have some injection of hotter basalt material, but there's some thermal or viscosity barrier where this material is not able to mix with our resident felsic material. So instead, what happens is our hot stuff down here is chilled against this cooler stuff. So there's thermal exchange, but there's no mass exchange. And the cooled, chilled surface right here can actually drive volatiles, so the exolution of bubbles, and actually cause volatile accumulation and can lead to eruption. So this is what we mean by thermal mixing. Both of these processes have their own chemical signature on their crystals. They both can lead to eruption. We just want to know which of these is happening at Baker prior to one of its eruptions. So we're looking for these two different processes with these plots. So coming back to our plot here, the majority of our data is being well described by this red arrow, which is that chemical mixing. So we know that mafic recharge at Mount Baker is definitely a prevalent process. So if we come back to our zoning pattern, our zoned crystal here, we can give a little more meaning to this zoning pattern, where the core represents the earliest stage of growth. So we have some plagioclase originating in this shared dacite reservoir. But then we know that this basaltic andesite that we see in the interior of our crystal has to be the result of this chemical mixing. So that's telling us that some mafic recharge happened, allowing for chemical mixing to happen, and then allowing for this interior part of our crystal to form. And then lastly, we observe this basalt rim. Well, that's telling us that there was likely a second recharge event that created this plagioclase rim that also likely actually initiated this eruption, since it's the final thing recorded in our crystal record. Okay, so I'm just showing you one example of how we're interpreting a zoning pattern in these chemical groups. Again, you don't need to digest all of this, but these are plots that my students, Desiree and Emily, have put together. And again, just to highlight the painstaking detail that these guys have given these crystals and these lavas is just so impressive. So they've put a lot of thought into decoding the processes that are happening prior to 4 different lava flows. And so I'm not going to go through all of these. We don't have enough time, but I will summarize basically what they found. So again, if we're thinking about 4 lava flows through time, our oldest lava flow, Dobbs Creek, we didn't really see evidence for mafic recharge. Instead, we're seeing a lot of evidence just for that thermal underplating process. But then Dobbs Cleaver, Swift Creek, and Sulphur Creek, we do see strong evidence for mafic recharge. So we know that mafic recharge is happening, and sometimes it leads to an eruption. So the main takeaways from this chapter is basically basalt recharge is a very common process at Mount Baker. Sometimes it leads to eruption, but sometimes it doesn't, right? We have evidence for recharge happening and not leading to an eruption. Then we do have evidence for recharge when it does lead to eruption. So we see evidence both for recharge and thermal underplating. And then another cool takeaway is that we see the same chemical populations in the lava flows through time, indicating repetitive processes and this long-lived magma factory beneath Baker. Okay, so that is addressing chapter 1, is basically what's going on prior to eruption, like what's actually tipping the scale. Now let's talk about what is the timing of those processes that we're recording in our crystals. So the way we get at time in a crystal record is through diffusion chronometry. And I think some of you are familiar with this method, as it's becoming more and more popular. But in case you're not, the way this works is we're basically exploiting the diffusion of elements across zoning boundaries. So if we have a simple zone crystal where we have a core and a rim, on the atomic scale, we would expect our atoms to be oriented in a way where one side of our crystal boundary is one element and the other side is a different element. And I'm showing that difference just by color here. Naturally, at magmatic temperatures, so when things are hot, our atoms will naturally start to jump from one crystal site to another. And so that jumping is what we call diffusion. And so in this scenario, diffusion is being driven by this chemical gradient where these atoms naturally want to find some sort of chemical equilibrium. So they'll diffuse until they reach some sort of chemical homogenization. So diffusion is great for us because we can use it as a stopwatch for magmatic processes. So if we have, for example, this zone crystal forming in a melt, if we were to take a chemical transect across that zoning boundary, we would expect that the core composition is some composition represented by this red color, and the rim is represented by this yellow color. And the profile from A to B here is this really sharp change in concentration. And so we call this a step function. But again, you guys know at magmatic temperatures, atoms are going to start to diffuse. And you can see our zoning boundaries here have now become fuzzy. They're less sharp. And our profile that was once sharp in concentration has relaxed in shape. So see how we now have this curved trend from A to B. So if we assume that our initial condition is this sharp step profile, we can calculate the amount of time required for this relaxed profile to form. And so a very easy analogy to compare this to is making a cup of tea. So initially we have a sharp boundary between normal water and tea water, but then given time and temperature, our tea has homogenized and is now able for us to drink. And so the way we actually calculate time is using a partial differential equation. So this is Fick's second law that basically relates the shape of the profile we observe to the rate at which diffusion of some element at some known temperature is diffusing to time down here. Okay, so the way we physically do this is by modeling diffusion in two different minerals. So we're looking at iron magnesium interdiffusion in clinopyroxene. And so again, we solve this differential equation with known boundary conditions, and we get some solution that looks like this. We don't do this by hand. We write Python scripts to do the math for us. So if you're not familiar with diffusion, it's actually pretty straightforward to teach. And I'm happy to share my code with anyone interested in this technique. And I wanna make the disclaimer here that for clinopyroxene, we do assume a step function initial condition. We don't actually know what that shape of the initial condition looks like, so we assume that step function, and so we're actually calculating maximum timescales here. And we're gonna use the code after this paper, Shamloo and Grunder in 2023. Okay, so that's clinopyroxene. We also model magnesium and strontium diffusion in plagioclase. And notice our partial differential equation here is actually a little more complicated because we have this whole other variable, which is anorthite content. So partitioning and diffusion rate in plagioclase is dependent on major element chemistry. So that adds a little bit of complexity to our modeling. So our solution is a little crazier, and we have to make other considerations such as trace element partitioning being dependent on anorthite, the rate of diffusion being dependent on anorthite. The initial condition is dependent on our melt that's in equilibrium with our crystals. So we have to have a good sense of the melt that was in equilibrium. And then we're also going to use the model after Jordan Lubber's work in 2022. So thank you, Jordan. We love your code. Okay, so what do I mean by eruption initiation time? So the whole last chapter, we were talking about eruption initiation mechanisms. So basically the timing is what we're getting after. So it's the duration of time between that mechanism and eruption itself. Or you can think of this as just the last magma storage where crystals are growing to eruption. And at Mount Baker, we have established that the majority of the time, this eruption initiation is from mafic recharge, and less occurrences is thermal underplating. Okay, so we have our zoned crystals here. So we have plagioclase, we have clinopyroxene. Down here, I'm showing strontium and anorthite content on this rim transect here. This is magnesium number on this clinopyroxene rim. And the key to doing diffusion modeling for eruption initiation is modeling from interior to the outermost rim, right? We are interested in the process that happened right before eruption. So we are modeling the very edge of the crystal. And then we also have to calculate temperature at which diffusion is happening. So we use mineral thermometry, specifically plagioclase liquid and clinopyroxene liquid after Peterka's paper. And we're using thermobar, which is a tool that Penny Weiser made in 2022. Okay, so getting into the actual data. So after all of that modeling, I'm happy to take questions about the modeling details, but for now, I just want to show the data that we get when we use this method. So this is time on the x-axis, and then our data here is binned by those specific lava flows. So remember, we're looking at a young lava flow all the way to our old lava flow. If you see a square, that's a clinopyroxene timescale. If you see a plagioclase, that's a circle. Dark circles represent strontium in plagioclase, and then light circles represent magnesium in plagioclase. And so the first thing your eye probably sees is the fact that the data has such a wide spread in time, and that the error bars are kind of big, and I see that too. And so I think a better way to visualize this data is through a cumulative density plot. So basically these lines represent the distribution of data for a single data set. And I think the obvious thing here is that our Dobbs Creek, or this green data set, is definitely on the longer end compared to our other lava flows. So we're seeing initiation timescales that are on the order of hundreds of years. But I want to make a note here. So notice, one, our data set's small. We only have 4 clinopyroxene timescales here. We weren't actually able to get plagioclase. And 2, what I'm not showing is these crystals are heavily resorbed. So we're not actually interpreting them as representing eruption initiation. Instead, we think that it's a small population of crystals that were residing in the magma, getting chewed up. And then as initiation was happening, they were kind of plucked and entrained in the ascending magma. So they're not really representing the final product prior to eruption. So we really need to go back and get some plagioclase timescales for this particular lava. But our other 3 lava flows, notice how their trends are very similar to each other, and the majority of their timescales are falling within a month to a year. So actually assigning some numerical values to these data sets. For our 4 clinopyroxene timescales, we get a median value of 340 years for Dobbs Creek. But then for Dobbs Cleaver, for 30 timescales, we get a median value of 3 months. For Swift Creek, 1 month, and for Sulphur Creek, 8 months. And then looking at this entire data set, my students basically determined 116 timescales. So this is a very impressive data set for this technique, and got a median value of 3 months. So while there's a spread in our data, if we look at the statistics of our data, it's telling us that our timescales are relatively short. So again, the idea was to compare these timescales through time. Now, Dobbs Creek, we couldn't really do that because of the small population of crystals, but for Dobbs Cleaver and Swift Creek and Sulphur Creek, we're seeing a consistently short timescales on the order of few months. Now, putting those data in context with other diffusion studies on arc volcanoes, so down here is all of our data, and the line style is representing the different mineral chronometer with the element next to that mineral chronometer. So here's all our data, again, in kind of the months territory. But then notice for other studies done in the Cascade Arc, so this is Mount Hood, this is Mount St. Helens, we have Lassen Volcanic Field, and Mount Shasta. Our timescales are in relatively good agreement with these other studies. Same is true for the Aleutian Arc. So these are some Alaskan volcanoes as well as an Andean volcano. So this is encouraging that the timescales we're getting are not outlandish. They are very much in agreement with other arc volcanoes. Okay, so a note onto why this technique is so important. So I'm very encouraged by seeing more and more studies like this. So this is a study that was published in 2012 that was looking at diffusion times from Mount St. Helens 1980 to 1986. And I want to draw your attention to this blue part of the data set real quick. So this is crystal ages versus time. And basically every black peak you see is a recharge event recorded in an orthopyroxene. And it's given a timestamp because this person has assigned diffusion timescales to these recharge events, the same way that we've done for Mount Baker. And what's amazing about this is that each time you see a perturbation or a recharge, it's associated with a peak in sulfur dioxide as well as seismic activity. So what this means is that these recharge events can be associated with unrest at the volcano that are detected through monitoring, and that these timescales from diffusion actually have meaning. So we can actually assign meaning if we have access to active monitoring techniques. So there's a lot of usefulness in this diffusion technique. And so this is becoming more and more popular, which is really exciting to me. So this was done at Mount Etna in 2011. And then, of course, Mount St. Helens, like I just showed you guys. There was this paper done in the same way in Chile. I've seen this done in Iceland, as well as a couple volcanoes in Alaska. And then more and more, Kendra Lynn's group in HVO is doing this for Kilauea, where one, it's constantly erupting, and two, we have really good active monitoring tools. So what this is telling me is, one, these mineral diffusion studies actually mean something. And if we are working on an active volcano with monitoring, this can be paired in a really useful way. And so there's a lot of merit to continuing these studies at active volcanoes. But a disclaimer, as exciting as this is, we certainly need large data sets on a single volcano through time to be able to start doing this. So that was our attempt here at Mount Baker, but of course I've only shown you guys 3 or 4 lava flows when there's a very long eruptive history at Mount Baker. So good start, but I think we have a long way to go. Okay, so that was chapter 1 and 2. Let's briefly talk about magma residence. And we weren't able to calculate magma residence for all of our lava flows, but let's talk about it for our most recent lava flow. So the way we're defining magma residence is the maximum total time a crystal is residing in an eruptible magma. And by eruptibility, we are talking about a viscosity that is viscous or not viscous, not too viscous that it's locked rheologically, but viscous enough where it can actually leave the volcano. And so a better way to visualize this is through a temperature time plot. So this is becoming a famous plot by Cooper and Kent, where the oldest recorded crystal growth is on our left and the youngest representing eruption is on our right. And then the black line here is basically the thermal record that a single crystal will experience in its lifetime. And so notice how it's fluctuating between the liquidus and solidus temperature. So it's constantly experiencing spikes in temperature and then falls in temperature, spikes and then falls. And notice that this red shaded region is where the majority of the crystal spends its lifetime. And so that was kind of the big takeaway of this paper, is that most of magma's lifetimes are spent cold or near this rheological lockup. And what we mean by rheological lockup is it's a temperature associated with a viscosity where things are too mushy, too solid to be able to mobilize and erupt. Now, why is this important for us calculating magma residence times? Well, if we find the temperature on the lower boundary of this rheological lockup, basically what we can say is that any time spent above 850, which is the temperature appropriate for Sulphur Creek, that is time that our crystal is spending in an eruptible magma where a lot of diffusion is actually being imprinted on our crystal. Anytime below that temperature is a non-eruptible magma where diffusion is not happening substantially enough to really contribute to our diffusion signal. So if we model at that lower end, we can get a maximum total time that our crystal was stored in an eruptible magma. Okay, so the details with magma residence time modeling is we are no longer concerned with the rim. Now we want to model across core to interior. We want the earliest record of that crystal. So we're getting diffusion profiles that look similar to the ones we were talking about for eruption initiation, but now we're really focused in on this core interior boundary. And then we're going to model at a temperature towards our rheological lockup for this composition of lava, which is 850 degrees Celsius. Okay, so here is the results of that diffusion modeling for magma residence. So what you're looking at is data binned by basaltic andesite and basalt end member. Remember, our Sulphur Creek produced a lava flow with 2 compositional end members, so that's what you're looking at here. We have magnesium and strontium in blue and red, and then the shaded horizontal bars are basically our 2 sigma air. And our vertical lines are the best fit time for that particular transect. And so something that might stick out to you is magnesium timescales are faster than strontium timescales. And that's a really common observation in this type of modeling, simply because magnesium represents the faster diffuser relative to strontium. That's why I'm showing this little hare and turtle here. So if we see timescales where magnesium is actually trending faster, that's giving us an indication that that diffusion profile, that curve I've showed you guys, is maybe not purely from diffusion, but there's also an artifact of crystal growth. And so that basically just complicates the way we're modeling these timescales. So it's something to consider as we interpret these timescales. But actually thinking about the numbers here, our magnesium data set is telling us that our residence time is on the order of 0.65 years. Our strontium is on the order of 11.5 years. And then looking at the data set as a whole for 46 timescales, our median value is 5 years, and our maximum here is pretty much on the order of a few decades. So that's relatively short. So what we're learning is Baker magmas are stored eruptible on the order of years, no more than decades. This is relatively short. So this is telling us that eruptible magmas at Baker are really short-lived. And lastly, we do have to consider that our magnesium timescales are shorter than strontium, and this might indicate a growth effect, which would merit a maybe more sophisticated model to calculate these timescales. Okay, so comparing our timescales from the Sulphur Creek lava flow to other arc volcanoes, we can see we're on the shorter end. So, right, we're over here, Mount Hood, St. Helens, Cerro Galán, these different volcanoes are trending on the longer side of time. Now, I think, just like face value, I would think that this difference in time is from the fact that these studies are from compositions that are relatively felsic. So this is rhyolite dacite territory where we're working in basaltic andesite territory, so much more mafic. So this might suggest that felsic magmas reside longer than mafic, but really I don't want to make that claim until we do more of these types of modeling on Mount Baker lavas. But as of now, we are trending towards the shorter end. Okay, we have learned a lot. So we have learned that the transcrustal mush system beneath Baker is long-lived. We see these similar processes in crystal cargo being erupted through time. We found that the timing between mafic recharge and thermal underplating is on the order of 3 months. And eruptible magmas are relatively short-lived at Mount Baker, so on the order of 5 years to a few decades maximum. And then before I let you guys go, I just want to take a couple more minutes of your time just to pose the question of now what? What is the broader impact of our work? So some of you may be familiar with this report, others not, but this is a threat assessment report published in 2018 by the USGS that basically characterized all the active volcanoes in the United States and assigned them a threat level. So I want to pose the question, if we're doing this type of diffusion work, how can we actually use our results to make decisions about active volcanoes? So I'm asking, how can we actually use this information? So if you're not familiar with this report, the way that we actually assign a threat level to a volcano is through hazard and risk factors. An example of a hazard factor is by going to a volcano and asking, okay, what is the maximum volume that this volcano has produced before? If it's produced relatively small volume eruptions, it gets a lower numerical score. If it's produced relatively large volume eruption, it gets a higher numerical score. So my question is there a place for the kind of things we've been talking about today in this numerical scoring? Like, would we assign a numerical value to eruption initiation mechanisms if it's volatile accumulation versus mafic recharge? Would we assign the fact that some of our eruption initiation timescales are shorter versus longer? If they're longer, does that get a smaller numerical value than if they're on the order of days? And then is there a place for magma residence time in this hazard factors, where if the window of time for eruptible magmas at a volcano is on the order of centuries versus decades, do those get their own numerical score? I think we might be a far way from this point, but I think still something worth talking about and starting the conversation about. But first, of course, we need bigger data sets to be able to start making these decisions. So that was our attempt here at Mount Baker, is try to assess timescales through time, but we need to continue to do this kind of work. And then we also need to standardize the methods across our community. So we need to share our models and codes with each other, and we also need to prioritize workshops for best practices. And these things are definitely happening. I'm just saying, continuing to prioritize them as we move forward to attempt to actually make decisions about active volcanoes. Okay, and then lastly, I'm almost done, I promise. What is the broader impact of our work here? And so something that me and my co-PIs are very proud of is the production of this Summer Institute, which is a place-based learning and research experience. We call it the Kulshan Summer Institute for undergraduates. And this is where we invite undergraduates to work with us at Western Washington University. And we're in pursuit of a single question the entire week, which is, how do we know Mount Baker or Kulshan is a volcano? And so this is in collaboration with Terry Plake at Northwest Indian College. And a lot of our participants are from Whatcom Community College, Western Washington, and also Northwest Indian College itself. So a lot of our participants are from indigenous communities where this volcano has been surrounding their communities since time immemorial. And so I pulled this quote, which is very meaningful to me, which is, "My tribe has inhabited the coast and foothills of Kulshan since before time was recorded. I would love to get to know her more." So I think that just highlights kind of the importance of this institute in just exchanging ways of knowing. And so we're in pursuit of this single question, which is, how do we know Baker is a volcano? So we take our participants out into the field. They learn how to use standard field methods, such as digging tephra up with a shovel. They use geologic rock hammers on lava. We talk about geologic maps. We take our students back into the lab where they make their own thin sections. They use a scanning electron microscope to look at crystals on a microscale. And then they also diffusion model. So I had a breakout group where my students actually are calculating the same timescales I'm presenting to you guys today. Our students are doing in this workshop using Excel. And so that's really exciting to give students the agency to calculate and contribute to our scientific efforts with this grant. And then on the final day, our students present their own personal story, which is always incredibly special for us as institute leaders, because we get to hear what this volcano means to our participants, and we learn so much and in exchanging our stories between each other. And so this is something we've been running for 2 years now, and we have every intention to continue to run it so long as we have funding to do so. Okay, so that was a lot. I really appreciate your guys' attention, especially on a Saturday evening. I'm happy to take some questions now. Thank you.
Thank you, Hannah. That was terrific.
Yeah.
Yeah, people can undo their videos and we can take some questions. I have some down, but I think we have some good questions, and we're recording them for, about, well, as long as you can go, at least 10, 15 minutes.
Sounds good.
So raise your hand if you have a question. If you don't, I have a few. Well, maybe I'll let people warm up. And one thing you mentioned, like that Baker has had calderas, big eruptions. Did you see any evidence or have a thought in that on how we could, say in the future we're going to have a small eruption, or it might be building for a caldera?
Yeah, that is a great question, and that's always a concern with these volcanoes. So statistically speaking, Mount Baker's had one caldera, well, to my knowledge, one caldera forming eruption, and more frequently it's had these effusive lava flows. So relatively speaking, tame, mild style eruptions. So if we were to get eruptive activity in the future, we can't predict what that will look like, but we can say that the probability will likely be one of those more mild style eruptions. But yeah, that is ultimately the goal of volcanology, is to be able to say what's the timing and style of eruption we would get in the future. So yeah, great question.
Yeah.
I got two.
Oh, Forrest, go ahead.
Yeah, two questions, Hannah, and I've been thinking about this for a long time, and it kind of goes in with your Go Rock stuff too. But let's go to Baker. Is Mount Baker being thought of as a volcanic center, like Lassen, where you've had a period of prolonged volcanism in this kind of central region?
Yeah, so we do consider Mount Baker. So when we talk about Mount Baker, I think the first thing that comes to mind is the, iconic stratocone. But it is a
Right.
volcanic field where we have multiple vents, not just from the summit, but around the summit and through the cinder cones that pop up without us really knowing where they're going to pop up. So yeah, we do think of it not necessarily distributed volcanism, but it is a volcanic field.
Yeah, I know this. Drawing on my experience from Lassen, that the Lassen Volcanic Center, it started off with a small caldera, not like Yellowstone but a small caldera, and then the stratovolcano formed. So that was stage 2, or the Brokaw stage, and then stage 3 was their dome field eruption, and that's when, eruptions, and that's when you got your chaos crags and Lassen dome itself, and some of the others, and anyway, the caldera part is done, the stratovolcano part is done, so now it's just the the dome field, and then maybe some of what Clint and Muffler called the regional volcanoes, which includes the cinder cones and shield volcanoes and so forth.
Yeah.
And I'm assuming the same thing applies up at Rainier and Baker and.
Yeah. So is your question, like, is it common to have caldera forming eruptions, or?
No, I was just wondering if Baker is kind of being thought of as the same as like Clint and Muffler described, Lassen. Again, a volcanic center, which in Lassen's case, and it sounds like Baker too, you've had a caldera and a stratocone.
Right. And also cinder cones. Just Lassen also has a bunch of cinder cones.
The cinder cones up there, and I think the shield volcanoes too, and I'm talking about Lassen there. You've got what Clint and Muffler call the regional. If you think of the Cascade, the dominant volcanoes in the Cascades of being, cinder cones and shield volcanoes. These smaller, volcanoes, monogenetic stones, and then it's interspersed with these larger volcanoes, as the Mount Shastas and Rainiers and I guess Brokaw and Baker, so on and so forth. So and then a lot of those cinder cones, like the quote unquote cinder cone, they are a product of magma mixing, where you've had what Clint and Muffler call the regional mafic magmas mixing and blending with the more silicic Lassen magma.
Yep, Forrest, it's hard to hear you because your microphone's going in and out. So I don't want to I want to give her a chance to ask questions from other people. Maybe we can do this more offline.
Okay, sure.
Hannah, can you try to answer quickly what he said? And I'd like to have some other people ask questions.
Well,
thank you, Forrest.
Yeah, thank you, Forrest, for your. I don't know what your question was, to be honest. If you could repeat it.
Yeah.
Or you can shoot me an email. I can share my email in the chat.
Yeah, we can share your responses later. We're recording this right now, so I don't I want to keep it moving if we can.
Sounds good.
Okay?
Sounds good.
Yeah. Sorry about the breakup.
Yeah. Carolyn, Terry, do you have any questions, comments?
Yeah, can you hear me?
Yes.
Okay, because I see I'm up there twice. So, regardless. So thanks a lot, Hannah. I really appreciated this. And I guess Thursday I was only able to see like part of the last part of your presentation. So
Yeah.
it's really nice to see some process-oriented possibilities in terms of speaking to how soon the next eruption might happen. And this is a really good time for you to talk to the people at CVO who are, well, the whole VSC that are, beginning this next gen hazard assessment project. So
Yes.
I'm only have been involved on the map representation end of things, but I know that people like Tom Sisson and Mike Klin and others are really excited to try to find some more process-oriented ways of figuring out what's going on. So
Yeah.
so it's great. I was going to say regarding the 1975 heating, reheating, or uptick of thermal activity.
Yeah, totally.
Have you thought about that in terms of what might have happened if things perhaps occur, change on maybe a decadal scale?
Right.
I think that Jackie Kaplan Auerbach, wrote a few years ago about how there was probably a magma body, rising or reheating or
Intruding.
can you speak to that a little bit?
Yeah, I love that you brought that up. Thank you. So we have thought about that. So if we're following the logic that these multiple recharge events are happening in the mush system, but they don't always lead to eruption, then
My dog.
it's possible that 1975 activity was exactly that, a recharge that's leading to this mixing of intermediate magma that maybe is now in that eruptive window that could be erupting later. Our initiation timescales are on the order of months, so maybe it's one of those recharges that doesn't lead to an eruption, but it could be a recharge that then is opening this residing period where we have magma residence for decades to come. So we could be in a window like that. Hard to say with the limited data we have, but that is something we have talked about in terms of like the broader implications of Desiree and Emily's work.
Mm-hmm.
Yeah, thank you for that question.
Yeah, I guess another question too is, at Mount St. Helens, and Mike Klin and others, and John Pallister have concluded, and I guess Adam Kent noted this at Mount Hood as well, that you can really goose a magma body by sending basaltic magma up into it, and that's
Totally
probably what happened in 2004 at Mount St. Helens, where and the chemistry of the 1980-86 magma lava, whatever, was pretty much the same as what we saw in 2004 to 2008. Mm-hmm. And so I'm wondering, are you presuming that was more of a thermal goosing rather than a chemical remixing?
For Helens, I'd have to, you're talking about Helens and no longer Hood,
St.
right?
Helens.
Yeah, for Helens, I'd have to see what the chemical populations look like. For Hood, that Kent study you're talking about, that is very similar to what we're seeing at Baker, which is mafic recharge, creating intermediate magmas and erupting, causing eruption initiation. But for Helens, I know one of my colleagues, Tyler Schleter, looked at those plagioclase crystals, and I think I'm faintly remembering that he did see evidence for recharge, but I don't want to speak with certainty without revisiting those data. But yeah, I think you should look for like Schleter 2022 or 23 is where he published that. Yeah.
Okay.
Yeah.
Terrific. Good answer. We have still a number of people. I don't know, Terry, you've worked with her. You have questions? And I noticed Lynn and Nick Zentner. Hello, thanks for joining us. If anyone has questions, we're still recording and you'd like some good questions for her. Terry, you want to shoot?
Sure, yeah. Thank you so much, Hannah. It was great to see Britt and everybody. And, we do have a student here who is part of that summer institute. Woohoo! So that's, yeah, that's awesome. I just had a question about magma sources. And my question is, with the change in chemical composition, being more basaltic, I've always assumed that more mafic magmas resulted from more of a tensional environment rather than a compressional. Is there anything that you have seen? Is there like a change in the kinematics or anything? I don't know. I mean, that's way out there, but
No, I love that. So, I mean, there's different tectonic regimes from the northern to the southern part of the arc for sure. And so like that stress field is different. On a local scale, like just thinking about beneath Mount Baker, I don't know how to get at those that kind of level of detail. That's not my bread and butter, but I think if we asked a geophysicist, they could possibly say something to that. But the point is, like, to initiate an eruption, really the recipe is you need to achieve some sort of overpressure. So you're exceeding some tensile force where the magma has nowhere to go but up. So
yeah.
yeah, so that's the kind of physical detail I can give you, but in terms of like stress regimes, that's more of a geophysical question. But yeah,
Cool.
I think that's so cool that you're thinking multidisciplinary like that.
Yeah, good question. For other questions, will anyone wants to ask a question, speak out or have your video on. Britt, you've had your video on. Do you have a question?
No,
No?
I'm just absorbing. This is a little above my pay grade just yet, but I have a lot to look at.
Oh,
excited to keep talking to you about this, Britt. We're glad you're on the team.
I have to say it was an excellent talk, Hannah. Really.
Oh, thank you, Mindy.
Really good mixture and really easy to follow and very important. One comment that you cut the effects of the volcano off on the Canadian border, and it definitely goes in to the Sumas Prairie and the Fraser area too. So
oh, okay, yeah.
Sure you're working with the Canadians on that.
Yes. we appreciate and acknowledge our Canadian friends.
Yes. I have other questions, but I'd really like to hear some questions from the other people who've listened. I am sure that Lynn or Nick have some question, and it would be great to join us. James and any of the others, I don't know you all, but you may have a question. Turn your video on and ask away if you wish.
James and Yusei are actually two outstanding undergraduates working with me on the Goat Rocks volcanic area. So they know all about my Mount Baker work. I'm really happy to see them here.
Well, it looks like we have Lynn popping up. Lynn, you have a question you want to?
And I have to apologize to begin with. I missed the very beginning of your presentation, so you may have covered this already. But when were the most recent eruptions of Baker?
So the most recent is actually an explosive eruption that produced the BA tephra, and that was 6 point something thousand years ago, so 6,000-ish years ago. And one of Sue DeBari's master students are actually currently working on that eruption and trying to put those crystals in the same context of the populations that we've been talking about today. So more to come on the BA tephra for sure.
Great. We're still recording, and are there any other questions? Well, if somebody popped your video up. One question I had was, what would you, in terms of monitoring gases, the gases coming off, what could you maybe learn from your crystallization studies for what gases or what might show up in the water that those crystals don't want? And
oh yeah. So yeah, that's a whole nother part of petrology that is super important for monitoring. So one of my colleagues, Madison Myers at Montana State, so she looks at diffusion of volatiles, so hydrogen and boron, like all these small elements, and she looks at melt embayment, so basically melt inclusions that are open to their surroundings. And she, the same way that I model diffusion in crystals, she's modeling diffusion in melt, basically representing the final ascent of magma when volatiles are degassing. So when hydrogen's diffusing out of the system and lithium and all, et cetera, So that can give you a time scale even closer to truly the final ascent. And so that kind of time scale, you can hopefully assign that with some sort of signal unrest. So sulfur dioxide flux or chlorine, any kind of measurable volatile at the surface could potentially be associated with that short of time scale. But that's not the techniques that me and my research group are using right now. We're using minerals.
Yeah, well,
Yeah.
That's great. One other question, and I don't mean to hog the questions, I want someone else, but we're thinking one of our field trips are going down to South America, and I noticed that in the was it the 9.5, was it 9.5 earthquake that they had down there in 64, was it? There was a volcano that erupted. Now there's people are always saying, will the big one cause the volcanoes to erupt or not? Could you detect it at all in what you're looking at? Just wondering if you might comment if we had maybe you would have 3 months in between the earthquake to the eruption. We just wondered if you could comment on the link.
So that has been talked about, that has been discussed in the literature, that you can have these external factors initiating eruptions. So not something internal to the magma, but rather an earthquake, like you're saying, which is responsible for the Mount St. Helens 1980 eruption. This giant earthquake happened, causing a landslide, and then the release of pressure caused this lateral blast. So yeah, it's certainly a possibility. What's tricky about that is it's hard to tie, at least in past eruptions, it's hard to tie if an earthquake is really the initiation eruption mechanism in the crystal record. Like your crystals aren't going to tell you, oh yeah, an earthquake happened. Like you have to use context clues and field work to confirm that that eruption was initiated by an earthquake itself. But yeah, it's certainly a possibility to initiate an eruption that way, for sure.
Well, that's great. One last question I always like to ask is what kind of big problems do you think really need to be answered there? And if we could give you all the money you would need, what would you like to do there?
To do at Mount Baker?
Well, yeah, or related to that in your career there.
Yeah, so I've been really interested in Washington volcanoes because again, I have the pleasure of living in one of the most amazing states in terms of active volcanism. So I think if I had all the money in the world, I would assemble an army of students to basically do these diffusion studies on as many crystals as we can with as great of chemical resolution as possible to create a robust data set of these timescales and start making statistical analyses of how these timescales really operate over the length of a volcano's life. And that's going to take a lot of time and a lot of work. So if I had all the time and resources in the world, that would be my passion project.
Well, that would be terrific. And I don't see any other questions.